Okay, this has been bugging me like crazy, and so I've been trying to figure out a simpler way of solving this complex problem with our arm hold at command. So essentially, the axle at the center of our arm counts how many rotations it has. It's not direct, it's driving a belt. So it's actually 900 rotations of driving the belt uh, will lift this thing all the way to the top. And so it's about 5 rotations for every 1 degree, give or take. It's not exactly 900, but let's just keep the math easy. We're supposed to have our worm gear is supposed to keep our arm level, and so the downward force of the arm shouldn't reverse the gearbox that's holding this in place. Only the axle in the worm that drives the motor from the motor would be able to shift that. So part of our problem is mechanical. But right now we're just thinking about the software problem. Okay, imagine that we can't prevent slippage, that it's always going to fall back down. And so we need to apply a steady force to keep it at whatever angle we're told to keep it at. And so we need a function that will dynamically adjust the power to stabilize it. And our PID control that we use to turn gyroscopically driven angles of our drive system isn't working particularly well because it's just proportional response. If I'm told to go up top, slam on the gas, and then slow down as I get here. But that has a problem of starting to clank around once I'm there. And that's this whole PID motion control. And that's the I and the D in PID to really smooth that out so it's real stable. I don't think we necessarily have to do that, because this isn't a time in which we're trying to shift a motion here and really trying to make that an elegant motion. Instead, we're just trying to find out what's the stable power we need to apply a normal force to hold at this particular angle. And so I don't think it is as complex as we've been assuming. So our arm hold at command is right here. Let's start this hold power at 0. So this is the steady power this thing needs to apply in order to keep its stable at to bear the weight of the arm and whatever the arm may be holding at the time. So the destination of the arm hold at, so what is it holding at? That's saved in the arm command. So the arm has the variable at what degree you want us to hold it at. So this is the actual command that obeys that number and holds the necessary force. We were using this not really PID. I'm going to fold this up. Let's ignore that for now. So the PID control that we were using, let's see if we can think of something much simpler. So the power that we're going to apply is whatever this is, hold power. So hold power. But before we set the motor to hold power, we need to adjust the hold power. Okay, so every time we'll run this a whole bunch of times every second. And each time we'll figure out if we need to adjust the power, and then we'll maintain the arm at that power. So the super simple thing we could do is, if the error is negative, that means I'm too high. This number where I'm at, let's say 500, minus where I'm at, let's say, is 900. That means I'm 400 too high. So it'll be negative 400. Because this number is bigger. And so if it's negative, I need to reduce my hold at. So this is the basic idea. If my error is negative, then I'll reduce my hold power by a very small amount. And if it's positive, then I'll increase it a very small amount. But then we still might get a ping pong effect as it oscillates between going a little bit too high and a little bit too low. So we could slow this down by making even smaller increments. Or I could nest these inside of another if statement and say only if the error is greater than 10, which is about 2 degrees. So as long as it's within 10, if it's within 2 degrees, actually, right, so if it's over 2 degrees, then we'll make an adjustment. But if it's under 2 degrees, don't bother making a change, we're good enough. These sorts of magic numbers we shouldn't keep right here in our code. Same thing with this adjustment rate. These would be great if we held them in a different place. And so we can do that. We can say robot map dot, and I have a angle tolerance, which is 2 degrees. And so I can multiply that by 5 degrees. Because that's a constant. That's not quite a magic number, because that's just for every degree, like we already talked about. Every 5 rotations is 1 degree. So it's 2 degrees times 5, and that'll be 10. So that's the same thing. And so if we adjust the angle tolerance, we can help tune this. And we can also try to make a robot, and so this could be an adjust power. I don't want to actually do that quite yet, because I have no idea. Until we test this, I could be, I'm tired after a long day of work. I could be missing a lot of stuff. So we'll need to test it, and if we see that it is working, but maybe we'll like to tune it a little better, then we'll move this a magic number in with the robot map, and we'll tune stuff over there.